We're looking at alternating infinite series, and specifically we're focusing on the alternating harmonic series. And this is part 2. We're going to look at how can you judge convergence versus divergence in an alternating series. We'll explore it with the alternating harmonic series. So here's the alternating harmonic series. You can see it in sigma form here, and you can see it expanded here. And the question is, does this converge or diverge? So let's explore this a little bit. If you focus on the partial sums, the sequence of partial sums, what that means is that you could kind of list out, uh, this summation from n equals 1 to 1 first, and then from n equals 1 to 2, and then n equals 1 to 3. So partial sums, you can do this kind of numerically. I'm going to do it graphically in a second, but just to kind of give the idea, the first partial sum would just be 1 because the first term is 1. The second partial sum would be the sum of the first two terms. So 1 minus 1/2 is obviously 1/2. The third partial sum would be the sum of the first three terms. Well, the first two added up to 1/2, and then when you add 1/3, go to common denominator of 6. We're looking at 3/6 plus 2/6. That's 5/6. So 5/6. And then when you add a negative 1/4 into there to get the fourth partial sum, now we're looking at what 5/6 is 20, or actually, no, I'm sorry, we can go to twelfths. 10 twelfths, and then minus 3 twelfths, so we get 7 twelfths. Okay, we could keep going if we wanted to. The idea is sometimes you can tell what the series does as it goes to infinity if you can see a pattern in the partial sums and what they approach. In fact, if the partial sums sequence approaches a specific value, then we know that the series converges to that value. But sometimes it's hard to tell just looking at the numbers there. And so here, I think a graph can be really helpful to help us see, not just for this series, but for all alternating series, what could be really useful. So if we start at our partial sum of 1, what I'm going to do here is plot the partial sums as a function of n, right? So the first partial sum at n equals 1 would be 1, right? And then what did we do? Well, we had to add a negative 1/2 to that to get the next one. So we had to come down 1/2 minus 1/2 to our next partial sum, which, I'm going to put that minus 1/2 just on the other side there, minus 1/2 to our next partial sum at n equals 2. And that brought us right here. Okay, and then what do we do next? We had our 1/2, we added 1/3 to that. So if we go up 1/3, 1/3 is less than 1/2, it's about that much, plus 1/3. That takes us to 5/6, and that's our third partial sum at n equals 3, and that's a value of 5/6, we said. And then if we went another one, we'd go down 1/4, which again is not as far as going up 1/3, so minus 1/4, and that should put us at 7/12 approximately. And again, that's the right here, this term, right? So there's our next partial sum with a y value of 7/12. And we could keep going in that regard. In fact, if we do, you might have noticed, every time that we go to the next term, we go back in the opposite direction of where we just came from. And we always go less far than we just went. And so every time we do this, we're kind of fine-tuning this range down, right? If this keeps going, we know, like, as we go forward, we're never going to get outside of this range of y values, right? And if we go a little further, now we're never going to get outside of this range of y values, and so on and so on. In order to converge on a specific value, so that we kind of need to have this trend, and there's two parts to this that are important. One is that that piece about we keep going back not as far as we just went, right? So we went down a fourth, but we went up a fifth, and a fifth is smaller than a fourth. And then we went down a sixth, and that's less than a fifth, and so on, right? So these terms have to keep getting smaller in magnitude. That's one thing. And the other thing is they do need to approach zero. If they don't approach zero, then uh, what's going to happen is we might just keep going back and forth, and we never quite zero in on a specific value. If they approach, let's say the magnitudes approach 1/2, or let's say 1/10, because I'm in a pretty small area here, and they never quite get to 1/10, but they get really close, then we might just kind of keep bopping back and forth between two values without ever kind of zeroing in on something. But if these values keep decreasing in magnitude toward a limit of zero, that is what is going to make this series converge. And so if you have an alternating series, that's the test. That's the alternating series test. And it's once you kind of get it, it's pretty easy to apply. So let's take a look. Here's our alternating series. And yeah, if the terms of an alternating series decrease in magnitude toward a limit of zero, then the alternating series converges. And that does happen here. We know that you can test it if you want to prove it for all n greater than or equal to 1. What we want to show is that the n plus 1th term is less than the nth term. So we could say the well, we could just say 1 over n plus 1 is less than 1 over n, right? That's a true statement, and that shows that the terms are decreasing in magnitude. And then we could also say the limit as n goes to infinity of 1 over n is 0, right? As n grows infinitely, these terms are approaching 0. I'm leaving off the alternator here, right? If you want to put it on there, you can. This part still works that way. With this part, you would want absolute values then. But the point is you can kind of leave it off because it's sort of like a separate part. It's what makes it an alternating series, but this is the part that gives us the magnitude. So these two facts show us what we need here. We are decreasing in magnitude, that's this, toward a limit of 0, that's this part. Okay, and so that's the alternating series test. If you want to know if an alternating series converges or diverges, you can show that it converges if it meets those two criteria. And if it doesn't meet those criteria and it truly is an alternating series, then it is going to diverge. And you could probably just use, if that limit is not the case, you could use the nth term test, show that the limit approaches something other than 0, that tests for divergence. Or if it's not the case that they're decreasing in magnitude all the way, well, there's a couple things that could happen there. First of all, if off toward infinity this is not true, then you won't have this limit that we need. And so again, you could do the nth term test, the test for divergence. Or if it's just not true at the beginning for, let's say, a finite number of terms, let's say 10 terms, that this is not true, you could cut off those 10 terms from the series. You could go from 1 to 10 and then do the series from 11 to infinity. And as long as this is true from there on, then you can show that the rest of that series is convergent. Obviously, the first 10 terms are convergent if they're finite, if there's no domain problems. And so you can still prove convergence that way. If you need to cut off some terms, that's always something that can be done with these.